Hi viewers, I am Sudhakar Chekuri, Assistant Professor of ECE Department. Today we are going to discuss about the sequential logic circuits. So as an introductory topic to the sequential logic circuits, let us have a brief comparison of the existing combinational logic circuits and the sequential logic circuits. The combinational circuits are defined as the circuits whose output variables are dependent on the inputs at that instant. That is, if we apply certain inputs to the circuit, they themselves will decide what the output is. In the sequential logic circuits can be defined as the output of variables at any instant of time are dependent not only on the present input variables but also on the present state, that is on the past history of the system. So here if we apply the inputs, we cannot say what the output is. The outputs also require the information what are the past outputs. For combinational circuits design, we do not require any memory elements because we are not going to store any data here. In the sequential logic circuits, we require memory elements because we are storing the data. Combinational circuits are faster because we are not using any clock signal. In the sequential logic circuits, we are using a clock signal. That's why they are somewhat slower in operational. Combinational circuits are easy to design. The sequential circuits are harder to design. Now let us talk about the basic building blocks of the sequential logic circuits. As we have discussed in the previous slide, the sequential circuits require the memory elements for the storage of the data. So the fundamental unit of the storage element can be called as a latch. A latch is having one or two inputs and having two outputs. And the fundamental property of a latch is that its two outputs are complementary to each other. That is, if one of the outputs is 0, the other one should be 1. Or we say like this, if one of the inputs is 1, the other output should be 0. And a flip-flop. A flip-flop is same in functionality, that is same as the latch, but the way how it operates is different. The difference between a latch and a flip-flop is the way how they are triggered. A latch is triggered by level triggering process and a flip-flop is triggered by the edge triggering process. For triggering purpose, we use an external clock. So if the clock is maintaining a level of 0 or a level of 1, and if the memory element is changing the state, then it is called as a latch. If the latch is changing the state for the clock level 0, then it is called as a negative level triggering. If the circuit is changing the state, if the clock is maintaining a level of 1, then it is called positive level triggering. The edge triggering is a sharp edge on the clock will change the state of the circuit. That is, a change from logic 0 to 1 or a change from logic 1 to 0 upon the clock will decide the state change. So a transition of 0 to 1 is called as the positive edge. A transition of 1 to 0 is called as the negative edge. So state change occurs for the memory element upon the positive edge. The triggering is called as the positive edge triggering. And if the state change occurs upon 1 to 0 transition, that is on the negative edge, then the triggering is called as the negative edge triggering. Now the types of latches or flip-flops. There are basically 4 types of latches or flip-flops are present in the sequential logic. They are namely SR latch or set reset latch, D latch or delay latch, T latch or toggle latch, and the fourth one is the JK latch. So in this lecture, I am going to introduce the SR latch. The SR latch, or to that matter, any latch can be constructed using two NOR gates or two NAND gates. So here we are seeing in the diagram the SR latch using the NOR logic. So here we can see the complementary output of the latch is connected to the one NOR gate, and uncomplementary output is connected to another NOR gate. So if you see the function table, how it works is when we apply 0 and 0 to the S input and R input, the present state will remain same in the next state. That is, if 0, 0 are the present inputs and present state is 0, next state will be 0. And if the present state is 1, next state will be 1. Now we change the input combination to S equal to 0 and R equal to 1. If S equal to 0, R equal to 1, irrespective of the present state, the next state will be the 0. When S equal to 1 and R equal to 0, the present state, even if it is 0 or 1, the next state will be 1. The combination of 1 and 1 is invalid because we are not getting the complementary outputs. Q and QR are not complementary outputs for this set of inputs, which is contradictory to the definition of the latch. So the 0, 0 condition, present state is same as next state. So this state is defined as the no change state. For 0, 1 inputs, the state is 0. So this is called as a reset state. For 1, 0 combination, the state is 1. So this is called as the set state. Now it is a time to discuss the D flip-flop. And here we are discussing about the edge triggered D flip-flop. So by slightly modifying the SR flip-flop or SR latch, we can derive the D flip-flop or D latch. That is, by connecting the S input to the R input by inverting, we derive the D flip-flop or D latch. So if you see the functionality of the D or D latch or delay latch or delay flip-flop, that it is defined in the function table. If clock is positive, if on the clock the positive edge is occurring or negative edge is occurring, then if D is equal to 0, irrespective of the present state, the next state is going to be the 0. If D is equal to 1, irrespective of the present state, the next state is going to be 1. When the clock is disabled, irrespective of the D input, whatever the present state is there, that state will be remained in the next state. That is, if it is 0, it will be 0. If it is 1, it will be 1. Next, we are going to discuss about the timing relationships that are associated with the operation of the flip-flop. The first one is the propagation delay. The propagation delay is defined as the amount of time a flip-flop takes for the output of the first flip-flop to travel to the input of the next flip-flop. Here, when there are number of flip-flops are involved in design of any sequential circuit, so clock is applied in common. So the time taken to travel for the clock from one stage to the next stage may differ sometimes, and this will result in a phenomenon called as the clock skew. That is, the clock skew can be defined as a phenomenon in synchronous digital circuit systems in which the same source to clock signal arrives at different components at different times. That is, the instantaneous difference between the readings of any two clocks is called their skew. Now let us see the applications of the flip-flops. The fundamental application of the flip-flop is the data storage, that is memory element. The flip-flops can also be used for transferring the data. Flip-flops are the basic building blocks of the registers as well as the counters. The flip-flops can be used for the frequency division purpose and also as a switch debouncer. Now the edge-triggered JK flip-flop. By connecting the complementary output of the SR flip-flop to the NAND gate along with the J input, and by connecting the uncomplementary output of the SR flip-flop, that is Q, to the NAND gate along with the K input, we can derive the JK flip-flop. Here we are studying the JK flip-flop in the positive edge triggering manner. The JK flip-flop differs from the SR flip-flop only in one case, that is for 00 case 01 and 10 it functions same as the SR flip-flop, and 11 combination is not used in the SR flip-flop. But here in the JK flip-flop 1-1 combination is also used. When 1 and 1 are the inputs, the JK flip-flop will toggle its output. And the function table or truth table of the JK flip-flop is like this. If the clock is not applied properly, that is positive edge is not occurred on the clock, then irrespective of the present inputs, the next state change will be same as the present state. And after the proper application of the clock and proper application of the inputs, that is for j equal to 0 and k equal to 0, it is called as the no change state. That is, if in the present state we have a 0, we get a 0 in the next state. If we have a 1 in the present state, we get a 1 in the next state. And the complementary outputs are complements. And if the positive edge on the clock occurs and 0, 1 are the inputs, irrespective of the present state, that is even if the present state is 0 or 1, the next state will be 0. That is called as the reset state. And if 1, 0 are the inputs, irrespective of the present state, the next state will be 1. This state is called as the set state. Now the new inputs combination, that is 1, 1, which was not used in the SR flip-flop, is here it is used. That is, on application of 1 and 1 as J and K, the present state will toggle. That is, if in the present state we have a 0, in the next state we get a 1, and if in the present state we have a 1, in the next state we get a 0. This is the functionality of the JK flip-flop. And lastly, the characteristic equation of the JK flip-flop. The characteristic equation is one which defines the state changes that are going to take place upon the application of the inputs. It is derived from the modified function table which was discussed in the previous slide. So here we take the first column as the present state, and in the next two columns the present inputs, and the last column is the next state outputs. If we minimize this using the K-map simplification as shown in the diagram, we get the characteristic equation to be Q of t plus 1 is equal to J into Q dash plus K dash into Q. So if we substitute any of the inputs and any of the present state in this equation, we can get any of the next state. And this was called as the characteristic equation of the JK flip-flop. Now it is the time to discuss the synchronous sequential circuits and asynchronous sequential circuits. Synchronous sequential circuits are the sequential circuits in which the memory elements are clocked flip-flops. And asynchronous sequential circuits are ones in which the memory elements are either unclocked flip-flops or time delay elements. And second difference is the change in the input signals can affect memory elements upon the activation of the clock signal. Whereas in the asynchronous side, the change in input signals can affect memory elements at any instant of time because here there is no clock signal. And the third difference is in terms of its speed. The synchronous sequential circuits are somewhat slower compared to the asynchronous because there are time delays involved because of presence of the clock signal. And here in the asynchronous side, there is no clock signal, hence it is faster in operation compared to the synchronous sequential circuits. And the synchronous sequential circuit design is easy compared to the asynchronous, and asynchronous sequential circuit design is difficult compared to the synchronous sequential circuits. And that's all for the presentation.